Okay. There we go. Right. Okay, that's fine. Hello, everyone. Well, anyone and everyone that's here. Hello. So there was someone suggested some stuff to talk about in my Discord, which was interesting. I like the idea about talking about action principles. Somebody mentioned Euler-Lagrange equations, but before that, there was a nice little result. I mean, obviously, please do just post stuff in the chat as we go along. But there was quite a nice little result. I thought it might be fun to talk about, which is it's a very straightforward little result. I mean, it's something that it came up in one of these courses I'm assistant teaching this term, and it's also something I spoke about with a very young student I teach, who is 7. So it's not going to be something too taxing, but it's a nice result anyway. So I thought I'd talk about that. This is about Platonic solids. So you might know that there are only 5 Platonic solids. These are 3D shapes that are made up of faces, regular faces, identical regular faces, and they're symmetric, so every vertex looks just the same as every other vertex. The simplest one I can draw is a cube. This is one example of a Platonic solid. It's not the smallest Platonic solid. The smallest one is the tetrahedron, but the tetrahedron is actually a little harder for me to draw anyway. Whereas the cube is quite straightforward. And there's quite a nice little proof. I mean, there are a couple of proofs, but there's one proof I like that through which we can show that there are only 5 of these Platonic solids. So only 5 of these 3D shapes that have faces of a regular and that are regular 2D shapes making up the faces, and they're all made up of the same kind of face. They're all identical faces. Okay. And we can sort of prove this using a nice little formula from topology, or a formula that talks about planar graphs. So for a cube, for example, what I'd like to do is I'd like to change the cube into a planar graph. So this is like a kind of a graph theorist's graph, not an XY graph. So I can take the cube and I can transform this into a planar graph. Planar just means 2D. So when I draw it, I can draw it in 2D without having to overlap arcs on top of each other. The arcs will only cross, they'll only meet at nodes. We won't have anything like, well, this one actually you can't draw in a non-planar way, but say if we had a few more nodes, you could draw one where there was no way of connecting up the nodes without having things cross over. But a planar graph doesn't have these crossing over points. So this is how we can draw a 3D cube as a planar or a 2D graph. Okay, this is one way you can draw it. There are other ways. And you can see that there are no crossing over of the arcs except at the nodes. Arcs only sort of split and cross at nodes. Okay. And there are certain properties of the graph that we can relate to properties of the cube. So these sort of cycles inside of the graph are called regions. And an important thing to note is that we also count the outside of the graph as a region that I'll call the exterior region. Then these dots we call nodes, and the lines here we call arcs. So you can see that the regions on the graph actually correspond to the faces on the cube, the faces on the shape. And you can imagine that because we have this exterior region, you can imagine that what we've done to turn this cube into this kind of 2D planar graph is we've sort of turned it inside out. We've stuck our hands through one of the faces and then pulled it inside out. Okay, so because we have this exterior region, that actually means that the number of regions is the same as the number of faces, because we've kind of got rid of one of the faces here in turning it inside out. But then, because we count the exterior region as a region, the number of faces equals the number of regions. Okay, and likewise, the number of edges this cube has is now represented by how many arcs the graph has, and the number of vertices the cube has is represented by the number of nodes the graph has. In fact, sometimes these points on the graph are also called nodes, but are called vertices, sorry. But I prefer to call them nodes. And there's a formula which is true for planar graphs, so true for graphs where there is no overlap of the arcs except at the nodes. And this formula says that the number of nodes plus the number of regions minus 2 gives the number of arcs. Okay, so you can check that that is true for the cube. So the number of nodes is 1, 2, 3, 4, 5, 6, 7, 8. The number of regions, well, this is the same as the number of faces, so that's 6. So that's 8 plus 6 so far, minus 2, that gives 12. So are there 12 arcs? Are there 12 edges on the cube? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, there are. Okay, so it works for the cube. And we're going to assert that it works for all planar graphs. That is, all graphs that lie in a 2D plane. And actually, the proof you can do to show this is also quite nice. So if you want to prove that this holds for all planar graphs, say you assume it's true for some, for some complicated, whatever it is, some complicated graph, something like this, which is planar but sort of a bit ugly looking. Well, what you can do to prove that this is true, if we assume it's true for this funny looking graph, the procedure you can follow is to first cut the arcs that form loops. So by arcs that form loops, I mean where you've got a node that is joined to a node by more than one arc, then you can cut one of these arcs. So this is another one we can cut. This is another one. So it's not just wanting to make it so that there's one arc between each node. We want to turn this thing into a tree. So we want to turn the graph into a tree. A tree is a graph that has no regions enclosed. It has no cycles. Okay. So we want to cut that too. And now this is a tree. There are no cycles in this graph. But you'll notice, well, maybe let me draw one of these back so I can show you. When you cut this arc, in cutting the arc, you sort of blend this region here into this region here. So every time you cut an arc, you reduce A by 1, but you also reduce R by 1. Okay? So when we do this step, A goes to A minus 1, and R goes to R minus 1. But because the formula has an A on one side and an R on the other side, it still stays balanced. So the formula is still true. What can we do next? Well, now we can start sort of cutting arcs and getting rid of nodes. So I can get rid of a node here. Oops. Get rid of a node here. And then I have to get rid of the arc that was joining it onto the tree. So now I've taken the number of arcs has been reduced by 1, but also the number of nodes has been reduced by 1. So you can see that in doing this, we can slowly just get rid of the entire graph. Well, that was the cycle I kept in earlier as an example, but I would have gotten rid of that before usually. But you can see if we keep reducing the number of arcs and nodes by 1, eventually we've demolished the graph. But the whole way through demolishing it, it stays true. Okay. So 2 is now cut off loose nodes and the arcs that are attached to them. And that takes the number of nodes to reduce by 1 and also the number of arcs to reduce by 1. But that keeps the formula balanced still. So that's a sort of proof as to how you can do this thing, by cutting these arcs first that forms cycles, and then cutting off the loose nodes at the end. You'll manage to show that this holds for all graphs. Okay. So that's a sort of justification of the formula. And now we can apply this to this graph here that is representing this particular shape. Okay. So for any 3D shape, the way we turn it into a graph is, like I said before, you kind of imagine you reach into one of the faces of the shape, and then you kind of pull it inside out. So you flatten it out into a 2D shape, and you get the graph of it. And then the things that translate from the 3D shape onto the graph are the number of faces on the shape become the number of regions in the graph, the number of edges on the shape become the number of arcs on the graph, and the number of vertices the shape has become the number of nodes on the graph. Okay? So our formula like this now becomes something like this. Where this is the number of edges on the 3D shape, this is the number of faces, and this is the number of vertices on the shape. Okay? But remember, the thing about the Platonic solids is this defining characteristic is that they're all made out of identical faces. So all of the faces that make up these 3D shapes should be identical, and they should be symmetric. So every vertex on the 3D shape should look the same, which you can certainly see is true of the cube. There's no difference between this vertex, and this vertex. And that should be the same for any Platonic solid. Okay, they should be symmetric about, rotating it into any other vertex. Okay. So we can introduce 2 more things. We can introduce S, that I will call the number of sides on a face. So every face is the same, remember, for these solids. So this is the number of sides a face has. For a cube, which has square faces, this number will be 4. And then I also introduce M. This is the number of faces which meet at a vertex. So for the cube again, now this will be 3. You can see the cube has got 3 faces that meet at each vertex. There's this face here, and this face here for this vertex. Okay. So what we want to find is the number of different ways there are of constructing a 3D shape that is made out of identical faces. And given that you make it out of these identical faces, how many faces you're allowed to have meeting at a vertex, and how many sides these faces are allowed to have. Okay, so we're interested in these numbers S and M. These will determine what the shape looks like. how many faces meet at a vertex, and how many sides each face has. Okay. So we can relate some of these quantities here to these quantities here. How can we do that? Okay, so the number of edges the shape has. Well, there are sort of two ways we can figure out the number of edges the shape has. If there are m faces that meet at a vertex, and there are v vertices, that means that the total number of faces will be v times m. Okay. But in just doing v times m, we've actually double counted the number of edges that are present here. Because if you think each edge is shared between two faces, okay, so we have to divide by a factor of 2 here. Okay, so v times m is counting how many total faces there are at each vertex. So if you like, if there are 3 faces here that are meeting, that means there are 3 edges connected to each vertex. But in counting this from the perspective of each vertex, what we'll end up doing, so from doing it from the perspective of this vertex and this vertex, we will double count this edge here. So we have to divide by 2 to get rid of that double count. Okay. What's something else we can do for the number of edges? Well, something else we can do is we can take the number of faces in total that make up this shape, and then we can think about the number of sides each shape has. Okay? So that is f times s. But again, in counting how many faces there are, which for the cube would be 6, and multiplying by how many edges each face has, we've again double counted, because each one of these edges is shared between 2 faces. So we'll count every edge exactly twice if we just do the number of faces times the number of sides to a face. So we have to divide by 2 again. Okay. And these 2 formulae here we can rearrange. So I can now find the number of vertices in terms of the edges and the number of faces that meet at a vertex. And likewise, I can find the number of faces in terms of the total number of edges and the number of sides each face has. Okay? And now if I put these things, these new expressions I've got up here, back into Euler's formula, which is this, remember this is only true for planar graphs, but we've sort of justified that Platonic solids you can always turn into a planar graph if you sort of stretch them inside out through one face. And that gives us 2e over m plus 2e over s minus 2 is equal to e. Okay? And now if we divide this whole thing by 2e, that gives us 1 over m plus 1 over s minus 1 over e is equal to a half. Okay. And I can rearrange this a bit again, just taking the 1 over e to one side and bringing the half to the other side. And now what I can say is that all of these things here have to be integers. M has to be an integer, S has to be an integer, and E has to be an integer. Okay, so I'm interested in integer solutions to this equation. And E, well, the more complicated the shape gets, the bigger the shape gets, the bigger e will be. Okay, but e will always be a positive number. So this entire right-hand side here will always be a positive number. Okay, that is certainly true. But I mean, this can, in theory, this can be as little as I like. You know, 1 over e, the more complicated I make this shape, 1 over e will get smaller and smaller as e gets bigger and bigger. So really the thing that must be true of this equation is just that 1 over m plus 1 over s minus a half must be bigger than 0. Okay, that is the kind of the bound on this equation. Or in other words, 1 over m plus 1 over s must be bigger than a half. Okay. And now we just have to find all of the integer pairs of solutions, m and s, for which this is true, for which 1 over m plus 1 over s is greater than a half. Okay. Well, so clearly m and s have both got to be bigger than 2. You know, if you only had, you can't have a face of a shape which only has 2 sides, where the sides are made of straight lines, or else, you know, it wouldn't close, or you would just have one line on top of the other line, and that's not a face of any kind of shape. And you couldn't have fewer than 2 vertices meeting, or you couldn't have 2 or fewer vertices meeting at faces, meeting at a vertex. The smallest number of faces you can have meeting a vertex has got to be 3. Okay? So these things have got to be greater than 2. Both of these. So you can just test some small values. You know that these things, there will be a cutoff. There will be a finite number of integers m and s for which this is true. As you go higher up in m and higher up in s, these fractions become smaller and smaller. And then after a certain point, the sum of the 2 fractions will no longer be bigger than s. Okay, so this already starts to tell us that there is only a finite combination of sides of a face and number of faces meeting at a vertex that will give you one of these Platonic solids. Okay. So we can just try a few. We can say, well, let's start with the number of sides of the face being 3. So this would be a shape with triangular faces. And well, if the number of sides of the shape is 3, let's try 3 of these triangular faces meeting at a vertex. So s is 3 and m is 3. Well, that gives us 1 over m plus 1 over s is equal to 2/3, a third plus a third. And that's certainly bigger than a half. So this pair does satisfy the condition. So that is allowed. Well, let's try another triangular faced one, but now let's try 4 triangles meeting at a vertex. Okay, so now you've got a third plus a quarter, which is 7/12. And again, that is greater than a half. So now you've got 4 triangles meeting at a single vertex on this shape. 4 triangular faces. And that's okay, that's allowed. But then if you try s is 3 and m is 5, so this is 5 triangular faces meeting at a vertex, then that gives you 8 over 15, which is also greater than a half. That is allowed. But then s is 3 and m is 6. Now we have 9 over 18, which is equal to a half, and therefore is not greater than a half. You know, that it's less than or equal to, but it's not greater than a half. So that doesn't work. These 3 are allowed. These are 3 kind of faces we're allowed to build one of these Platonic solids with, but not the other one. So then you can move on and you can try, what about making a shape with square faces? So the number of sides on each face is 4. Well, again, we can try 3 square faces meeting at a vertex. So, I mean, it's obvious this will be a cube. That's what a cube is. A cube at each vertex has 3 squares meeting. And adding that up gives you 7 over 12, which is greater than a half. So that is fine. But then if you try S is 4 and M is 4, so now if you think about 4 square faces meeting at a vertex, that isn't allowed because that'll give you a half. And a half is not greater than a half. So then you move on and you think about, what about pentagons meeting at a vertex? S is 5. So we try M is 3 again. And that again gives us 8 over 15, so that is allowed. But then if you try S is 5 and M is 4, that gives you 9 over 20, which is not greater than a half. So that is not allowed. And you can see now that we've reached here, S is 5 and M is 3. Well, before, up here, we had S is 3 and M is 5. So 1 over S plus 1 over M is the same as 1 over M plus 1 over S. So you can commit yourself that when you start trying higher ones, none of these are going to work, okay? Because none worked for S is 3 that were higher than this. So these are the only ones, these 5 here. 1, 2, 3, 4, 5, okay? And these all have particular names. So the S is 3, M is 3 one is the tetrahedron. The S is 3, M is 4 is the octahedron. And the S is 3, M is 5 is the icosahedron. So this is 5 triangles meeting at a single point in every vertex. Then S is 4, M is 3, that is the cube. And S is 5, so this is one made out of pentagons. 3 pentagons meeting at every vertex. That is the dodecahedron. And that's it. So these are, you know, the only kind of totally fair regular dice you could make. You could make a tetrahedral dice if you wanted to. That would be a 1 in 4 probability. An octahedral dice that would be a how many sizes an octahedron have? What, 1 in where was our formula for F? I can't remember. F was 2E over S. Well, an octahedron has got 6 faces, doesn't it? I think it's got 6 faces. I mean, we can work it out. 1 over E is 1 over M plus 1 over S minus a half. So for an octahedron, that's 7/12 minus a half. So that is 1/12. Oh, so an octahedron... Oh, of course. Okay, yeah, it's 4 triangles meeting at a point, not 3. Yeah, so an octahedron has got 12 sides to it. Oh, no, it's got 12 edges, sorry. It's got 12 edges, so then it's got 8 sides. Oh, well, that's why it's called an octahedron. That was really dumb of me. Okay, yeah. So yeah, an octahedron has got 8 sides, hence the name, I suppose. Icosahedron, well, I don't know what that prefix means, so I can't figure that out from the name, but that's 8 over 15 minus a half. So that is 16 minus 15, 1 over 30, 2 times 30 divided by 3. 20? Is an icosahedron 20? Surely that's a dodecahedron. Dodec sounds like 20-sided. I don't know. It doesn't matter. Anyway. But the point is, these are the only regular dice you could make that have the identical faces, so would be very fair dice. I mean, there probably are some ways you can construct dice that are fair without having a regular number of faces. Maybe where you've got sort of a smaller probability of landing on a particular smaller face, but maybe there are more of them. So it will average out to give you the right probability. That's probably an interesting problem. Trying to think of irregular shaped dice that are still fair. I'm sure you could do that. But anyway. So yeah, that was just a little thing I thought was quite nice and quite interesting. As I said at the start, this was something, well, it's one of the little things that's taught in one of these courses I'm TAing this term, and I also spoke about it a bit with a 7-year-old that I teach. A very bright 7-year-old. I don't think most 7-year-olds would, would find this so straightforward, but they are a very bright 7-year-old. Okay. So does anyone have any other stuff, little things they wanted to talk about? Someone posted in my Discord about talking about like Euler-Lagrange stuff, which is quite nice. Because these things are interesting, these action principles. Generally, they're only... Hello, Slayer Darth. Generally, I think action principles are talked about in a very kind of teleological way, as in this is how you compute an equation of motion from a Lagrangian. But I think there's a lot of deep stuff there, philosophically, about why these things work. But you can kind of prove they work. For Newton's laws, anyway. So, Newton's second law sort of gives you Hamilton's principle. So Hamilton's principle is about the action being stationary along the path or along the motion that a particular system will take. And you can show that directly from Newton's laws. So Newton's second law in one dimensions, the most general way you can write it for a potential anyway, for a conservative force, is to have the mass times the acceleration is minus the derivative of this potential. Okay, so where I'm going to use dashes here to mean a derivative with respect to x, and I'll use dots to mean a derivative with respect to time. Okay, so this is Newton's second law. And we can use this to try and prove Hamilton's principle. Okay, this is where it comes from. You can think of it as coming from Newton's second law. So to help with that, I'm going to define the average kinetic energy along a particular path. And I'm going to define that, I'm going to define it as the time average. So if it takes some time, large t, for a particle to go along this path, x, between two endpoints, then the time average is given by this, where xt parameterizes the 1D path the particle takes. This is all in 1D. We'll do the simple case in 1D. Okay, so that's the time average of the potential. This little tilde on top will denote the time average for me. And then we can think of the time average of the kinetic energy. So this will be 1 over t of the integral between 0 and t of 1/2 m x dot squared as a function of t with respect to t. So this is just the mean. I mean, it's the continuous version of the mean using integrals rather than sums. The mean is the sum of everything divided over how many everythings you have. Well, in terms of continuous variables, it's the integral over them divided by the range of your integration. Okay, this is how you find the mean of a continuous variable. And now we can think about deforming the path of the particle. So xt, as I've written it here, this is the path the particle takes. So, say the particle starts off here at x initial at t equals 0. and it takes some path through space to reach x final, which is at t is equal to capital T. Oh, that's going to get cut off a bit, isn't it? Okay. So xt is what parameterizes this path. You can see that t is a continuous real variable that runs from 0 up to capital T, and depending on the particular value of little t I plug in, will tell me which x position along the path I'm at. Okay. Now, of course, I know the way I've written it, x is 1D, and I know I've drawn this in 2D, but, you know, thinking about it as a 1D problem, it's kind of like the particle might go back, it might sort of, you know, it might jitter along a bit, and then eventually reach the end point. That's what it could look like in 1D. Okay. But typically people always sketch it in 2D as a little wiggle. So I now want to think about taking this path and sort of deforming it in places. So just maybe wiggling it a little slightly the wrong way. So changing it from the real path the particle takes to a path it doesn't necessarily take. Something that might be non-physical. Okay. And when I do this little wiggle, so I'm going to write this wiggle as the path plus a wiggle. And the wiggle might depend on time. Okay, the particular part I wiggle will depend, you know, maybe you can see I wiggle it slightly more here when the particle is at this time, quite a bit here, but then there's not really any wiggle here. So the wiggle will depend on time itself. And when I do this wiggle to the path, that will also induce a wiggle in the potential and the kinetic energy, or rather the average potential and the average kinetic energy. So I want to find, given I do this wiggle, what is the corresponding wiggle in the potential and kinetic energies. So let's first find the wiggle in the kinetic energy. Sorry, I mean the potential energy. So that wiggle is going to, we still have the integral here, but now the wiggle, so the change in the potential energy, will be the potential energy evaluated along the new path. So this is the path xt plus delta xt, minus the potential energy evaluated just on the original path. The change will be the final after the wiggle minus the initial before the wiggle. Okay. So that is going to be v xt plus delta xt. Yeah, exactly. We will end up Taylor expanding. Because delta x we'll assume is a small wiggle, we will end up only looking for things at first order. Exactly. So minus the original kinetic energy. And this is still all integrated over t. Okay. And as theoretical phys suggested, what we can do now is we can Taylor expand this first term here. So because we're only providing a very small wiggle on top of the original path, we can Taylor expand this function, or technically functional, v. Okay, but in 1D a function and a functional are really not actually that different. Okay, it doesn't really matter how we treat it. So this will become v of xt plus v differentiated with respect to x times delta xt. Okay. So that is what this term here becomes, doing the Taylor expansion on it. And then we still have minus this term here. So still minus v xt. And you can see that this term here will cancel this term here. Ooh. So we just end up with this. Okay. No hot? Oh, no higher order terms. No, so, I mean, we're only taking this as a small deviation away from the path. Okay, we're free to do that. So we don't need to think about the higher order terms here. Okay. The point is that this thing should be stationary. You know, this thing shouldn't change when I sort of induce this wiggle here, when I vary the path by some amount delta x. Okay. We only have to think about small deviations from it because it's, you know, it has to be sort of locally stationary. So for delta x being small. So that is our variation. That is how the potential energy changes when we do a wiggle in the path. Now let's do a wiggle in the kinetic energy. So again, that is going to be the kinetic energy evaluated now at this point rather than at xt, minus the kinetic energy evaluated just at xt without the wiggle. Oh, forgot the 1 over t. So that is half m, and then we've got the time derivative, so the x dot of now this entire thing here. So that becomes x dot plus delta x dot. Okay. X dot t plus delta x dot t. And then we take away the initial kinetic energy. Okay. And now we can expand this square root here. And when we do that, we're only looking for terms that are first order in delta t again. Yeah, and there is a dt on this delta x here. You're right. Okay. And so when we expand this out, we'll get an x dot squared term here, but this will cancel with the x dot squared term here. So when we do it all to first order, we just end up with m times x dot t delta x dot t. Okay. That is what we get. But we don't want it in terms of the variation of the velocity. We want it in terms of the variation of the path. Okay. Oh, you meant at the integral. What did I... Oh, right. Oh, I see. Oh, yeah. Thank you. Okay. So I can rewrite this slightly. It turns out that the variation of the x dot, so the variation in the derivative of x, is actually the same as the derivative in the variation of x. Okay. And now what you can do is you can integrate this term here by parts. So you know this integration by parts formula that looks like this. u dv dx. dx is uv minus integral v du dx. dx. Okay. So if you apply this integration by parts formula, you can turn this integral into mx dot t delta xt evaluated at big T and 0 minus the integral between 0 and t of m x double dot t times delta x, all integrated with respect to t. Okay. And now this term here will vanish because something I didn't mention earlier, but when you're finding that the variation in this path, you assume that the endpoints are fixed. Okay, so we're looking for the path between these 2 points, xi and xf, but the points xi and xf, you know, this initial position of the particle and the final position of the particle, we say are fixed. So the path does not vary at these points. It's only between them it varies. So that means delta xt is 0 at these boundaries. So we just end up with this. Okay, this is the variation in the average kinetic energy. So it's a little confusing. I've used T for the kinetic energy, capital T, and I've also used T for the time that this thing is in motion. Perhaps I shouldn't have done that. But anyway, this looks very much like deriving the Euler-Lagrange equations. Well, it is, actually. But rather, what we're doing instead is we're deriving Hamilton's principle from Newton's second law. Okay. What was that? Oh, thank you, Lonhart, for following. So we're not yet deriving the Euler-Lagrange equations. What we're doing is we're deriving Hamilton's principle, which says that the action of the motion of the particle should be stationary along the path that the particle takes. Okay. So this is sort of the step below that, the slightly more fundamental step. So let me copy down the equation for delta Vx we had here. Now we have these two equations for the variation in the average kinetic energy and the variation in the average potential energy along the path. But you'll notice that what is inside here of these integrals is precisely what we had related from Newton's second law. So remember, Newton's second law, I'm just going to call Newton 2, was mx double dot is equal to minus v prime, where v prime is the x derivative of the potential. Okay. So you'll notice that if another way of writing Newton's second law is mx double dot plus v prime is equal to 0. So you can see that if I take the variation in t and the variation in v, the kinetic and the potential energy, and I subtract them. So if I now consider the variation in t minus the variation in v, what I get, I could pull the 1 over t out, I can pull the integral out, and I end up with mx double dot plus v prime, all times delta x, integrated with respect to t. Okay, this is what we end up with. But from Newton's second law, we know that this should be identically 0. Okay, yes, exactly. This is why the Lagrangian is t minus v. This is what we're showing. We're kind of justifying why this particular quantity, the Lagrangian, why it time integrated gives the action which is stationary. Okay, this is what Hamilton's principle is. So this thing here is 0. So in other words, for what we've shown explicitly here is that for 1D motion, the variation in the time average of the kinetic energy minus the time average of the potential energy along the path of the motion that the particle takes is equal to 0. Okay? But remember how we defined the time average of kinetic and potential energy. They were these time averages, these integrals over t of the potential energy at a specific point in the motion and the kinetic energy at a specific point in the motion. Okay. So, if you like, in this equation here, we can also say, of course, that the variation in t, where t was this time period, this time in which we were considering the particle motion, t times that is also 0. So I can get rid of this annoying factor of t here from the time average. It doesn't matter. So if I define this new functional, or function, I'll call it. We haven't explicitly said what a functional is, but for the case of 1D, it's simple enough just to say function, okay? We can define this thing here that is the time integral now of the kinetic energy minus the potential energy, where this is V, this is T. The time integral of this thing, the variation of it. So if I change this path slightly, if I change the path xt into xt plus delta x plus some wiggle in the path, the wiggle in the action will be 0, no matter what the wiggle I give in the path will be. Okay. And these statements here, this is really Hamilton's principle. Okay. Yeah, sure, it could be V minus T. Yeah, it wouldn't make a difference. I mean, you can see that, even in the Euler-Lagrange equations. So we haven't derived these, but the Euler-Lagrange equations are like this. So, I mean, swapping L for minus L is just like multiplying the entire thing by minus 1. It doesn't do anything. The action is a very flexible thing. You can always add a constant, or you can add even a function, as long as it can be written as a total derivative to the action, and it won't change things at all. It won't change the equations of motion. But these terms, these total derivative terms, are actually very important. So in general relativity, for example, the action you use to derive Einstein's field equations, this Einstein-Hilbert action, this usually lacks a boundary term, one of these total derivative terms you're free to add on. But it's actually very important to add that term in making the problem of varying the action well posed. This is called the Gibbons-Hawking boundary term. And it actually has important consequences when you're considering things like phase transitions between spacetimes, or thinking about black holes. This boundary term is very important, but it doesn't change dynamically. It doesn't change Einstein's field equations, but it is important nonetheless. So that's a good comment to make, that the Lagrangian itself is in no way unique. There are lots of things you can do to it and add to it that will not change the equations of motion. Okay. And these action principles are, they're enormously important in physics. So we've shown explicitly here that you can formulate Newton's laws in terms of an action principle. So this thing here, I should have said, those that may not have seen it before, is called the action of the motion, so the action of the path, and along the path that this particle actually takes, that action is stationary, meaning when I vary the path of the motion by some small amount, delta x, remember we added, then there's actually no change in the action itself. This quantity s here will not change. And it seems that this principle is you can apply it pretty much, well, not pretty much everywhere, but I mean it has enormous applications in theoretical physics. But like I mentioned earlier, it's kind of only really done in a sort of teleological way, where you're taught how to do things with it, how to compute things. But why it is that the universe seems to like these action principles is, I think, an interesting question. Not one I have a satisfying answer to. Why the universe seems to like either maximizing or minimizing things You know, I think that's something interesting to think about, because in using this stuff, what you do is you can formulate pretty much, anything. Well, I mean, you formulate all of your stuff in quantum field theory. Even in general relativity, you can formulate the problem of finding these equations as variational problems. So problems where you have a particular action like this, and you know that this action is stationary along the sort of particular path, or for the particular equations you want to find. So it instead becomes a question of sort of working backwards, like we did here, where you know the physical law, the thing that must be satisfied, and then you just need to find the action that is stationary when these equations of motion are satisfied. So it's working backwards instead. But then in having this framework where you deal with actions and Lagrangians instead of equations of motion, this is the language that particle physics works in, is in terms of actions and Lagrangians. Okay, so it's enormously important, and it's a very powerful tool. And you can formulate all sorts of things with it. I mean, you can use an action principle. A bit of a silly proof is to prove that a straight line is the shortest distance between 2 points. That you can find with an action principle. Why though? Why is it useful, or why does it work? I mean, I think the thing you do is, well, particle physics uses it because it's convenient, because it's much easier than dealing with these equations of motion, and as well, there's a very nice way you can use the action to calculate things in quantum field theory that you would like to calculate. So it's called Feynman's path integral approach. So we spoke about sort of wiggling the path here. So the black path we've got here is the path this classical particle actually takes. Okay, so when I do this red wiggle, when I change the path, this takes me further away from the real path the particle takes. Okay, it reduces or increases the action, but along the classical path, the black path here, the action, this time integral of the Lagrangian, is stationary. It's at a maximum or a minimum. Okay, but in quantum mechanics, it's a lot more complicated than that. So now, all of these crazy paths that are not the classical path, they're not, if you were dealing with, a large object, if you were talking about motion of a tennis ball or something, then that particle would only take the classical path. This is the path that classical physics, Newton's laws, remember, that we used to get to the action principle, say that it should take. But in quantum mechanics, all of these crazy paths we get by varying the action are now very important, and they will all contribute to the probability that a particle will get from here to here. Okay, so there's a way of thinking about quantum mechanics that is called the path integral formulation of quantum mechanics that makes use of this principle of least action very heavily. And I think in terms of why particle physicists use Lagrangians and action to compute things, I think it's just that it's much more convenient to calculate things in this way than it is using, say like the Hamiltonian picture of quantum mechanics, which I think would be quite difficult to calculate these things. They're equivalent. They're sort of equivalent pictures. Using a Hamiltonian and a Lagrangian, they're just, they're two sides of the same coin up to a Legendre transformation. But yeah, I'd say it's probably because it's computationally convenient, and there is this interesting interpretation, or not interpretation, there's this interesting way of calculating things in quantum mechanics that makes use of the action principle. Okay, but now it's quite a different use of the action principle, because now even all the crazy classically non-physical paths all will contribute. And bizarrely, they all contribute equally. So the crazy paths contribute just as much as the sensible path. Okay, so this path contributes to the probability just as much as some absolutely nuts path does. The only difference is they have a different phase attached to them. Okay, so now there's like a complex phase factor that is in front of each one of these paths. But actually doing these things mathematically is not very well defined, because in order to calculate this probability or this amplitude that a particle will go from here to here, you have to sum over an infinite number of crazy paths. So you end up writing down this path integral, this integral over all of the different paths the particle can take, but it's something you could never compute. Yeah, the phase does matter. So the phase is actually given by the value of the action. Okay. So I mean, along each one of these paths. So the black path I've drawn here is the classical path. The action S takes some value, but along any other path, it also has a value. So along this path, the action, where I've defined it as the time integral of this Lagrangian, whatever it is, will give us some number. Okay. Now, the only special thing about the classical path is that when I deviate from the classical path, my action either will increase or it'll decrease, because it's a stationary point. It's either a maximum or a minimum. But all of these other paths, you can compute the value of the action for them just as straightforwardly. And actually, it's the value of the action for the particular path that is the phase factor. The phase factor, is like e to the is xt. So that is the phase with which these paths add up. But like I said, in terms of actually computing this thing, it's totally crazy. You can't actually do an integral over an infinite number of integration variables, because that's what it is. It's like if you divide the path up into an infinite number of tiny little integration variables, you can think about this first sort of instant of time. The particle is anywhere along here, then the next step it's anywhere along here, and you end up having to integrate over an infinite number of variables for every single little one of these time steps, and it gets it'll get totally crazy. Okay, but yeah, that's how this is applied anyway to particle physics. And yeah, it's computationally very convenient. That's why people use this in particle physics. Okay. So, and it's also used in relativity. So, I mean, there's an action, well, like we did last time when we were trying to derive, when we were doing the stuff about Mercury's orbital precession, we wrote down an action that corresponded to the space-time interval between these 2 points. So in GR we have the space-time interval ds squared, which in flat space-time is just like this. But then, for example, we've seen around a black hole or any spherically symmetric matter distribution or point mass is given by the Schwarzschild metric. This is just telling you another way of calculating line elements, of finding intervals in this curved space-time now. Now the action principle takes a different form. So now it just says that the proper time that is experienced by somebody that is moving through this space-time. So now, you can imagine they are moving through this curved space-time. The path that they'll take through the curved space-time is the path that extremizes the proper time they feel. Okay, so the proper time to write this space-time interval in terms of proper time, this is just equal to minus d tau squared. Okay, the reason for that is that in the frame in which the person measures proper time is defined as the time coordinate you measure where you're at rest in that reference frame. Okay, so where your spatial position with respect to that frame is not changing. So in other words, dr and d omega will be 0. So there, the space-time interval that this person that is moving on the path, the reference frame that is kind of tied to them as they're moving along this path, will measure no spatial difference along the path because it's fixed with them, but it will measure a temporal difference, which is this proper time. So now this action principle is stated as the action that I'll call S, where now if we integrate over the total proper time, so this is the total time the person feels along the path, total proper time. Now this is stationary. Okay, you can formulate, you can find the geodesic equations in this way, as saying that whatever the path, whatever the geodesic the person takes through this curved space-time, the proper time they experience has got to be extremized, minimal or maximal. Okay, and that gives you the path that they will take. So this is why, this is why last time we called this quantity here, with the dt squared, etc. We called this the Lagrangian. Why is it minimized or proper time minimized or maximized? Physically, why it happens. I'm not sure. So again, you can kind of think about it in a teleological way, as I've been saying. So you find that you know what the equation should be. You know the equation should be these geodesic equations. So if you go back and find, well, what action principle, which action, when extremized, will give me these equations, and it turns out this action is the proper time. But I'm sure there is a more satisfying explanation for this, because it seems like something you could easily understand or try and think about, but I can't think why it would be. So in classical mechanics it's t minus v, and in GR is proper time. Yeah. So in classical mechanics t minus v, extremizing that will give you the equations of motion for your classical motion, and in general relativity, extremizing the proper time, or equivalently you could think of it as extremizing the space-time interval, will give you the equations of motion. Okay, I mean, it's like I mean, the way people sort of will think about it, you could think about it. I was just about to say, it's like how. So you can also derive. Yeah, exactly. You can also derive equations in classical optics from. Oh, what's it called? It's another action principle. It's about that light will travel along the least. Light will take the path of least time. Wherever it goes. That's it. Yeah, Fermat's principle. That even in forgetting about relativity, if you have light propagating, through any medium, whatever, the path it takes will be such that it minimizes the amount of time between those 2 points. So I guess you think about it. You can think about it in that way. It's very similar to that, except now, instead of light, it's matter will take the path that minimizes the proper time between those 2 points. And that's the same thing light will do. So not just matter. I mean, if you have light traveling along these geodesics, light traveling in curved space-time, light will find the path that minimizes well, you have to be careful because it's not minimizing the time as seen by somebody outside. It's minimizing the time as experienced by the person that is moving, or maximizing. I shouldn't say minimizing, because it could actually also be maximizing. It just has to be extremal. Yeah. Yeah, it probably is something related to that. I'd have to think about it a bit more. Well, so that's the thing. You can't really think about observers moving at the speed of light. You can't think about proper time for light because it's not defined. There's no instantaneous co-moving reference frame in which light has 0 speed. So that doesn't quite work out with it. But I think the logic is similar. It's you're extremizing the proper time experienced by, if it's a massive thing, so not light, the proper time experienced by this matter moving between the 2 points. Yeah. Yeah, it is interesting. These action principles are all very interesting, and they've got an enormous range of applicability. Yeah, I want to think more now about why you could think that the time has to be extremized, the proper time. I mean, a lot of a lot of these things in nature, they tend to either want to take a maximal or a minimal value. It's not usual in nature for things to want to be intermediate. Things always want to be either minimized or maximized. Entropy wants to be maximized. Energy wants to be minimized, or potential energy wants to be minimized. Yeah, exactly. DS is exactly that. That's the right picture to have. DS, the interval, is like this 4-dimensional length. This equivalent of length in special and general relativity, and it has to be extremized. So yeah, it's very in analogy to how the shortest distance between 2 points is a straight line, except now, of course, your space-time is curved. So now the shortest distance is not a straight line. It's a path that sort of will go through these curves and valleys in the space-time in such a way as to minimize the length that is used. But again, like I say, it doesn't necessarily have to minimize. It could maximize. It just has to extremize it. As far as I know, I'm pretty sure it can maximize or minimize. I think the only condition is that it has to extremize it, which has always seemed odd to me. It makes it seem less sort of physical, that it could be minimal or maximal. Even just in like classical mechanics, thinking about how the Lagrangian, is t minus v, like a simple 1D problem. It has to be minimal or maximal. It's not, is it to do with the negative sign? Ah. Oh, well, yeah, that could be interesting. But I think even though if you kept it as, you could pick a convention, as T minus V, which is the standard one, and I think even then it could either be maximal or minimal. That's a very good suggestion though. That, I don't think it quite explains it though. I think it can truly be maximal or minimal. Hmm. Yeah. Yeah, I have to think more about that. I mean, all of these, this is something we picked to talk about fairly last minute, but I think there's a lot to think about with it. Like I keep mentioning, this is always done in a very, here's how you compute, here's how you find, this is why this is useful way. That is one way of looking at it, but the you know the slightly more philosophical way of thinking, well, why should it be that way? Why should these things be maximized? Why should they be minimized? Is also interesting. Because to me, that it doesn't, even in the most simple thing we did, where we were just proving this, Hamilton's principle for 1D motion, it makes sense if you prove it using Newton's second law, but it's not entirely intuitive why it should be stationary. I mean, the way I used to think about it was, t minus v, the integral of t minus v with respect to t is kind of like, it gives you a measure of how much the energy is chopped and changed between kinetic and potential. So saying this is minimized is like saying, the universe doesn't like to switch back and forth, switch the energy from potential, switch it back to kinetic when it doesn't need to. It likes to transfer kinetic to potential in an efficient way, where your energy you don't unnecessarily spill over. You sort of reach a balance in an efficient, pretty quick way. But I don't think that's a good way of thinking about it, because, as we were saying, this thing doesn't necessarily just have to be minimized, it has to be extremized. So it could be maximized, which totally throws that out the window. It's the fact that it's minimized or maximized that makes, I think, these things hard to think about. Do I think there's a more fundamental way? Well, I did. Well, yeah. Well, I don't. I don't know actually. I think if there was a nice way of understanding it. I mean, this sounds ridiculous, but what I mean is, if there was a nice way of understanding it, I feel like I would have heard it by now. But in all the courses I've taken, in all the reading, studying this I've done, I've never found a nice, convincing way of thinking about it that it makes intuitive sense. So maybe there isn't a way, or maybe people just it's not kind of been. Maybe it's just not the way it's taught. It's just not the way physicists tend to think about it. But certainly, from my education and my thinking about this, it's not something I've come into contact with much about. Well, why is it, intuitively? But I mean, then a lot of things in physics are not completely intuitive and are just our tools or our mathematical consequences. So, I don't know. Yeah, I think that's probably quite typical. So on the one hand, I think it makes sense that the universe overall would like to maximize or minimize things. That is something physical that is often happening. Like I mentioned, entropy maximized. Systems like to maximize their entropy. They like to minimize their potential energy. They like to, you can think of thermal equilibrium as like minimizing temperature variation. Lots of things can be phrased as minimizing or maximizing. So having, I think, an action principle that relies on extremizing, minimizing or maximizing something is probably quite natural, because the laws of nature seem to be that way. There are lots of things that like to maximize and lots of things that like to minimize. So I guess it does make sense, but then I suppose for the specific cases, I'm not sure. I think possibly the proper time one. I can envision having the most satisfying interpretation, but other than just stating it as a principle, the proper time of an observer will be extremized along the path it takes. I can't see where that principle would come from. Yeah, exactly. That's what I mean by the universe tends to minimizing or maximizing things. Oh, as in, is it like a potential? Well, yeah. I mean, so a potential is I guess, an example of that, where if you deviate something, it will tend. A potential well is something that has been extremized locally. Locally, it's been minimized. Um, that's, I guess, a potential well is like the simplest example of this, if you like. But it doesn't. A potential, just thinking about minimizing a potential, doesn't take into account dynamics, so to speak. Because if you have a lot of kinetic energy, it doesn't matter what your potential is like. You're not just going to settle to the bottom of it. You can roll around in it. You have to kind of lose energy somehow to get to the bottom. Whereas this is like minimizing in a dynamical way. So you're not just finding a particular point. Minimizing a potential is like finding a point that you will go along. Whereas this is like minimizing a function or finding a path. But it's very similar. You're right. It is like that. But this stuff is it's not quite as simple to think about like that. Yeah, these things are interesting. I want to have a more of a think about the GR one though. I think that's what I'll do later. Probably in the shower. That's when I do most of my conceptual physics thinking, is in the shower. I'll have a think about proper time. And why it would be extremized. Yeah, because that seems to me the most displeasing thing. The fact that these things can be maximized or minimized, even for a particular definition. So for t minus v, that could be maximized or could be minimized. If it was just one or the other, if it was just minimized, that would be fairly satisfying. Yeah. Well, anyway, maybe I'll leave it there now, because if not, I'll just be thinking more or less in silence on the stream. So yeah, we'll probably leave it there. I don't know if anyone is here, who's here saw. But I posted in the Discord. I was thinking about doing like a kind of streamed study session thing. Oh yeah, thank you. Thank you, XTRexy, for linking the Discord. Thinking about doing like a streamed study session or work session thing, where I could basically just stick the stream on while I'm doing work, and then sit in one of the Discord channels, the voice channels on the server, and if people wanted to join to also just do work, not like as a proper stream thing, so I wouldn't record it or wouldn't upload it to YouTube. Just do our. Well, I probably wouldn't show my own work, just because I think I would find it I'd find it uncomfortable showing my own work, just because I'd feel like people would be watching me struggling more than usual. I mean, I struggle with some of this stuff, but I think I probably wouldn't show my own work. But I could always put the board up if there was something somebody asked that I thought I could help with. But yeah, I don't know. It might just be a way to. I'd try and put a bot in the chat that could like cue music or something, so it would just be kind of a sort of a chatting, chilling, working. And I mean, it would be nice for me, because certainly if I don't know something, yeah, exactly, it would be like a library, just like a study session or like a work session. But yeah, it would be nice for me as well, because if I didn't know something, I could ask someone and they might know it better than me, which is a very real possibility. So yeah, I don't know. Maybe I don't think maybe I won't schedule it because it might just be kind of spontaneous, or maybe I'll think of a time to schedule it, but it would be quite a relaxed sort of not very intensive stream. But yeah, if anyone else has any thoughts on that, feel free to let me know, or let me know in the Discord, etc. But yeah, I reckon I'll leave it there now. I'm quite eager to go and think about this stuff now. But okay, thanks very much for joining, everyone that did join. And I'll see some of you on Thursday for some Mario Kart. Okay. Okay, bye everyone. Bye.